Hi, my name is Fiona, and I am a sophomore biology major. Fun fact about me is that I have been Irish dancing for over 12 years. I would like to be a chemistry mentor because the chemistry mentors that I had in 101 and 102 were extremely helpful when it came to their review sessions and providing us with additional practice material and answering any questions that I had. And I really want to be able to provide that to students because I felt that that program really, and the students that were in it, really helped better my experience in the course, and I want to be able to do that for future students. And also I've had several positions as a tutor, both in high school and this past year, and those have really been great experiences. I've enjoyed those positions, and they've really helped me learn how to teach all kinds of students with all kinds of learning styles, but I've never really had the opportunity to teach my own peers and to communicate material in upper level science courses like chemistry. So I'm hoping that this experience would help me enhance my skills when it comes to teaching in subjects such as chemistry. And acid-base titrations are one of the hardest parts of the Chem 102 material, so I thought it would be most appropriate for me to demonstrate one of those problems. Okay, so this problem is an example of a weak base being titrated with a strong acid. And overall, the question is wanting to know what is the pH at the equivalence point. So the main thing we need to remember about equivalence point is that that is when the moles of the base are equal to the moles of the acid that have been added through the titration. And this here is a neutralization reaction because the base is accepting the protons from the acid that is added to then form the conjugate acid and water. So by forming water, it's neutralizing those protons from the acid. So we have 30 milliliters of cyanide, and it's a 0.150 molar concentration. So that means we have 4.5 millimoles when you multiply those of cyanide. And since the equivalence point, like I said, they're going to be equal moles, so, and we have a 0.1 molar hydrochloric acid solution. So we need 45 milliliters in order to have 4.5 millimoles of the acid. So I'm going to write that here, 45 milliliters hydrochloric acid. So since it's a neutralization reaction, they're going to react to completion to then form the same amount of moles of the conjugate acid. So now we need to find the new concentration of our conjugate acid in solution. So we had 4.5 millimoles, and we know that we had 45 milliliters added of acid, and we started with 30 milliliters of base. So in total, we have 75 milliliters now. So by dividing those, we get a new concentration here. So now all we have in solution is just this weak acid and water. So it's this just now becomes a simple weak acid dissociation equilibrium question. We can use an ice table for this. So this is our concentration here that we just found of our weak acid. These are initial concentrations of these, and since they all have a stoichiometric coefficient of 1, this is going to be our change. So our final equilibrium concentrations will be so. And according to our equation sheet, the equilibrium constant for this acid dissociation is 6.20 times 10 to the negative 10th. And the equation for this, as we know, an equilibrium equation is products over reactants. So like this is our equation. And then if we plug in these equilibrium values, we will have x squared, the numerator, and 0.0600 for the denominator. And we're going to leave off that negative minus x to save us time, so we won't have to use the quadratic formula, because we know that there's going to be less than a 5% dissociation because of how different these two values are. So when we solve for x, we get 6.10 times 10 to the negative 6 molar. And since x here, we said, was also equal to the hydronium ion concentration, we can just take the negative log of that to find our pH. So ultimately, we're going to get 5.215 for our pH, and we're going to use 3 decimal places because the molarity that we used here had 3 sig figs. There you go.